Hello, welcome everyone, and welcome back to CS700, Computer Science of Continuous Data, Algorithmic Foundations of Numerics. So now we have talked a lot about real computability and real computation, complexity, but today we want to start putting all the theory into practice. So let me show you the slides. Right. So here we are. Imperative real programming. That's chapter 6 of our course. And it will cover the following aspects in arbitrary order. First, we'll recall while programs. While programs, as you know, as we have introduced and considered them for discrete, complexity, and computability recap, are while programs over natural numbers. And then we want to extend that, to generalize that to while programs over real numbers. And we will see that this is actually pretty difficult. And instead, we will consider while programs not over the real numbers only, but while programs over three combined structures: natural numbers for counters, for example, real numbers, because that's the data we want to process, and in addition, a new data type for logical values with representing the Kleene logic. So not Boolean with two valued, but three valued Kleene logic. And we will introduce while programming over these three data types. And then we'll consider some example programs in this new paradigm while programs over three data types, namely integer rounding. Now, integer rounding, as you know, is discontinuous and therefore uncomputable in whatever model, reasonable model of computation we consider. But the workaround is to consider non-extensional, or also called multi-valued integer rounding. And we will see two programs that achieve that. First, a naive program, which takes kind of exponential time, and then a fast program, which performs this rounding process in polynomial time. Polynomial, remember, we always consider in dependence on the binary length of the input. Then we consider an example program computing the exponential function in the rigorous sense. That's the whole point of why we introduce all this, which is a transcendental function. So this exceeds really the algebraic computation paradigm. And we consider an example program for root finding of a given function. And as you recall, bisection cannot achieve that in a total sense. So we consider trisection, which involves a multi-valued operation. And then we consider the matrix determinant computation, again with a multi-valued operation for pivot search. And then we finally formalize while programs over these three structures: natural numbers, real numbers, and Kleene logic, and prove that these are actually Turing complete. They can express precisely and only those functions, real functions, that are computable in the original sense. And as you recall, the original sense is pretty inconvenient. The original sense means converting sequences of numerators of approximations to sequences of numerators of approximations from input to output. And this is a great definition. It has many great properties, such as structural properties, but it's very inconvenient for actual numerical programming. That's not how numerical scientists think or would want to program. This is kind of the stream computing approach. And in this chapter 6, we instead pursue the imperative approach that people in numerics, uh, any numerical programmer basically thinks in these terms. But now we provide this thinking with a rigorous foundation. Okay, so let us recall while programs over the natural numbers. While programs over the natural numbers have are composed from these operations initialized with 0 or 1, adding, subtracting but avoid negative numbers, dividing by 2 and rounding to obtain an integer if the original number was odd, uh, concatenation of programs, and this eponymous while loop that gives the name of the programming system. While variable xj is different from 0, execute this subprogram. So the loop is executed as long as the loop variable is strictly positive. That's a different way of formulating it since we're talking about natural numbers. Now we want to extend that to real numbers. And right, so if we want to compare natural numbers, then we can of course express that by testing for positivity using that positive difference method. And we can also express more advanced programming constructs such as if then else uh, using this while loop. So for simplicity, we only introduce while loop, but for practical programming, of course, one wants a more convenient construct, but this can be expressed using the while loop in this way, namely trivially. So if x is non-zero, then comparing x to t means that also t is non-zero, so the while loop gets executed, the body gets executed, and then as part of this additional instruction resets the loop variable so that the next time the loop tries to get executed, the loop condition is false and the loop is terminated so that the loop body is executed precisely once if x is positive and not at all if x is 0 to begin with. And can also express tests kind of the opposite, whether x is, so this is whether x is non-zero. The test whether x is 0 can similarly be expressed using the already introduced test whether x is positive in this way. And here I use the return instruction, which is not part of the language, but instead this sequence of operations, which is internal abbreviation, is to be inserted, is to be considered as an abbreviation for this instruction, for this comparison, not as a subroutine call. Okay, and right, similarly, for loop can be expressed using a while loop in the standard way that you all know and that you're all aware of. In this way, for loop means n ranging from k to l, including provided that l is equal or greater than k. If l is less than k, then the for loop is not executed at all in this semantics. Yeah, and that's pretty standard. But as I said, now we want to extend this while plus program model of computation over natural numbers to the real numbers in order to process the real data. And our goal is to define while plus programming over the real numbers in such a way that it captures precisely those real functions that are computable in the original sense with the stream transformation semantics, which is inconvenient but has structural advantages. So we want to find an equivalent programming approach that captures the same real functions, but using which is more amenable to how humans program, and they program not, they think not in terms of streams, but instead in terms of imperative operating on real numbers. And here's a first attempt, and uh, um, the full disclosure, this first attempt will fail. So the first attempt is to just replace the natural number as data type underlying our previous while plus program with a data type of real number, which includes the natural numbers. So that seems like a great first idea, and actually that the literature had considered this, but the problem is about the semantics of the real operations, which cannot be naturally extended to from natural numbers to real numbers, because as you know, the comparison here is suddenly becomes undecidable when we talk about real numbers, right? We proved that comparison is undecidable over real numbers. So if we design a while plus program over real numbers in this way, we can define whatever we like, but it's going to be unrealistic. It cannot be implemented. So what we did here is take the addition, which is no problem over real numbers. Real addition is computable. Now we can modify the positive subtraction. So previously we were constrained to non-negative integers and had to make sure that the subtraction returns 0, even if the mathematical result were negative. But now over the reals, that's no problem. And also division now becomes much more elegant. Of course, we don't need rounding, but the comparison, that's a huge obstacle to arrive at a realistic and Turing-complete wild-plus programming language over the real numbers. So how can we fix that? One way is to modify the original real semantics and make it a partial semantics, because as you recall, partial semantics of comparison is computable. So here's the partial semantics. If x is greater than 0, then the return value is a logical value true. If x is less than 0, negative, then the logical return value is false. And this is the crucial point. When x is equal to 0, this is what makes the real comparison undecidable. And then in this case, the return value is not an actual return value, but it's a special symbol called u for unknown. So u is a special part, and this is what makes what extends the Kleene logic beyond the Boolean logic. Boolean logic has only true and false, and the Kleene logic has this additional, it's a three-valued logic, has this additional third value unknown. And this value unknown has a very special semantics. We cannot compare for unknown. Otherwise, if we could compare whether the value of the Boolean of the logical of a logical expression is equal to u, then we would recover the whole problem. So testing logical value in the case it is equal to unknown will again not return anything. The partial semantics of comparison is just carried over, or put differently, it's a lazy way of evaluating this comparison, right? So in this case, the comparison, the result of the comparison, result in quotes, can be assigned to a variable of type Kleene logic, but now the variable's value cannot be tested without causing stalling computation to stall. And also let me point out that this value of the Kleene logic has a meaning which is subtly different from the mathematical notion of undefined. So this notion, for example, applies to division by 0, which is, as you know, is undefined, whereas the value of the comparison is mathematically defined, but computationally unknown. So here, this division by 0 is mathematically undefined. This comparison by 0 is mathematically defined, but computationally unknown, and therefore this symbol refers to computationally unknown, and this symbol refers to mathematically undefined. Subtle difference. Right, so we considered in previous examples for multi-valued comparison something which we call soft comparison, right? Since comparison is discontinuous and therefore uncomputable, we had relaxed that and introduced a multi-valued way of comparing whether given a real number is positive, and that this was called soft comparison. And the value of the soft comparison, Boolean value is true if the real number x is positive or not too negative, as being indicated by this parameter z, where z is now an integer. And imagine z to be a very large integer corresponding to a high precision. And similarly, the return value is false if x is negative or sufficiently close to 0 in this sense. And as you can see, there's an overlap, right? So if x is equal or close to 0, then both conditions hold. And this is what makes the soft comparison multi-valued, as you recall. So here you see the picture. There's an overlap. It's not a function. It's a multifunction. It's a non-extensional function when x is very close to 0. And here's the picture that we use to indicate multifunctions and the different kinds of restriction. So, and remember that we introduced this soft comparison because that's what renders the comparison computable. And we're going to incorporate that as part of the real programming language because of the to kind of prevent the partiality of the naive comparison, which may lead to an to partial programs only. And also integer rounding, we need to somehow make a workaround because integer rounding, whether it's rounding down or rounding up or rounding to the nearest integer, it's in either way it's discontinuous and therefore uncomputable. So if we were to introduce while programming over the real numbers in any of this way, we cannot include the integers as computationally as we would mathematically, because we cannot, for example, round. So instead, what we do here is we consider while programming over all three data types: integers, real numbers, and the Kleene logic. So, and we already saw how to modify the real comparison and such that it returns a value of type Kleene logic, not a Boolean value, in the type Kleene logic. So here are the three data types supported by this new kind of while programming: integers, which are agree with mathematical integers. So this is a full agreement. There's no wraparound like bytes. Having a wraparound, these are the full integers as are implemented, for instance, with big num in Java. Then there are the real numbers, which again coincide with the mathematical data type of real numbers. Again, full coincidence, no rounding as with floating point numbers. So this is the way that numerical programmers generally think when they write code, and only in the second thought look at what happens due to all this rounding in floating point. And this new programming language system kind of takes away all this burden from programmer, and they can now finally write code in exactly the same way that they naturally think about. It's very intuitive. And then the third data type, as already mentioned, is the three-valued Kleene logic: true, false, and unknown, where true and false can be kind of checked, can be subject to loops or if then else. But if the value is undefined, unknown, u, then any evaluation will stall and will not return a value and will be partial. So we kind of shift the partiality of the comparison into the partiality of evaluating expression or variable of type Kleinian. And here's the truth table of the Kleene logic for negation, for conjunction, and for disjunction. And you see that for the Boolean values, it coincides with the Boolean. So the negation of false is true, the negation of true is false, and the negation of unknown is still unknown. The conjunction of false with anything is false, even the conjunction with unknown. That's interesting. So if one of the arguments is unknown and we make a conjunction with false, then the result is suddenly becomes known and naturally becomes false, right? Whereas the conjunction of true with unknown remains unknown. Okay, similarly here, it's a symmetric operation after all. And for disjunction, it's kind of the opposite. So for Boolean arguments, it coincides with a Boolean disjunction. But when one argument is unknown and the other is true, then the value, return value is defined and is true. Whereas if one argument is unknown and the other is false, then the return value is unknown. So this is a very well-known three-valued Kleene logic, which captures nicely the exact semantics of real comparison that we, the way we defined it. And now we have can already start writing programs in this three structured over these three structures, but we need another connection. So connection between these structures is comparison between real numbers returns Kleene values. So that's a connection between these two. And the other connection between these two is the error embedding. So this is a subtle point. So we don't consider and allow embedding integers as real numbers. So if you have an integer, mathematically, this is also can be considered as a real number, right? So 3, integer 3 is also real number 3. But for reasons that become clear very soon, we embed the integers not by the identity, but by the exponential function. So z becomes as an integer is identified with 2 to the z as a real number. And this is helpful because, as you recall, this is the kind of error bounds that we usually have. Just only we usually call them 2 to the minus n with natural numbers, but it's actually much more natural to call them 2 to the z with integer z. Okay, and using this embedding, now we can make our mathematical expressions well typed. So carefully distinguishing comparison between integers and real numbers are not prohibited. We have two kinds of comparisons. One is comparison between integers. That's our usual comparison that we know from our classical while programs. And we have comparison between real numbers, but no comparison mixing between them, nor any implicit type conversions. Instead, explicit type conversion that raises the given integer to the exponent of this power of 2. So for example, here, there was initially, we were kind of fuzzy about the semantics of this expression, and now we should and we can become more rigorous, and the comparison will now reads like this. Okay. And one reason why we introduced this embedding and not the identity embedding is the following theorem. The three sorted structure, the structure with three sorts, integers, real numbers, and Kleene logic with this new undefined value um, is, and with this kind of error embedding is decidable. Now, remember what it means for a structure to be decidable, more precisely what it means, I should say, the theory, the first order theory of that structure is decidable. It means that there is an algorithm that, given any statement in the first order logic over that structure, tells whether this statement is true or false. True or false. And this is something unusual, as you may recall, because, for example, for integers, this is not true. The first order theory of the integers is undecidable according to Gödel, right? And also the first order theory of the rational numbers is undecidable according to Julia Robinson. So here we have something highly unusual. We have a structure with a decidable first order theory, and that hinges crucially on using this embedding and not on the identity embedding. And the point is, let me emphasize that we prohibit integer multiplication. Well, we have to. If there's integer multiplication, then immediately Gödel strikes and says that's already undecidable. But by excluding integer multiplication and only allowing integer addition and subtraction, this is where the so-called Pressburger arithmetic without multiplication, and that is decidable. So already this part, yeah, that part is decidable. That has been well known, Pressburger arithmetic. But for real number, of course, we do need multiplication. So if there was the identity embedding, then we could still express integer multiplication after the embedding using the real multiplication. And then we would also again get undecidability. So to maintain decidability of this structure, even with real multiplication, without integer multiplication, it is mandatory to use an embedding like this, because this embedding really, as you see, converts integer addition into real multiplication, and thus uh, uh, avoids including integer multiplication after the embedding. So that's one important reason why we use this way of embedding integers into real numbers. And the other reason is, as you recall, because these are the common error bounds that we use. So in order to express the error bounds, we actually need such a kind of embedding. Okay, so that's a theorem, and now we can start writing programs, except for, as you recall, how can we prevent this? How can we write total programs when the comparison, the real comparison is now partial, right? So if we have any program that involves real comparison in this rigorous sense, then there will always be cases where this comparison becomes an equality, and then the program will be only partial, will stall for such input. So, and only, well, if it's a non-trivial program. And the way to prevent that is to introduce some non-extensional new primitive, which we call choose, and choose receives a certain number of arguments of type Kleene. So here D is some integer, positive integer, and this is a D-array kind of function. It's a multifunction which receives D Kleene logic arguments, lazy, evaluated, unevaluated, and returns the index of one argument which is actually true, right? So if the jth argument is true, has value true, then it returns j, and if there are several of the arguments have the value true, then it returns some, any such j. That's what makes the operation multi-valued non-extension. And if none of them is true, then it's actually simply undefined. And now we don't need the soft comparison anymore as separate predicate, because we can express it using the partial real comparison in combination with this choose operation, namely in this way. So observe, this is a first interesting application of the choose operator. In this case, it's a binary version. It receives two arguments of type Kleene, right? So there's a comparison between real numbers. This is a real number, and according to this embedding, this is also a real number. And same here. So there are two comparisons of real numbers, and the return type of these comparisons is of type Kleene. And observe that this is exactly capturing these two cases, namely the second case here and the first case. And so according to the semantics, if the first case is holds, if the first case is true, then it returns the index of the first, which is 1. Minus 1 gives 0. So indeed, this gives the same value. This has the same semantics as our original soft comparison. In this case, whereas if the second argument evaluates to true, then the return value here is 2, index 2, minus 1 gives 1. So indeed, this gives the same semantics as here. And that, again, let me emphasize that there's an overlap, right? So we had here this overlap when x is very close to 0. And this is also the case here. So whatever value x here has, it will always, at least one of the two expressions will be defined. That's important. So, and since at least one of the two arguments is defined and true, right? At least one of them is true. Therefore, the whole expression is always defined, resulting in a total but multi-valued comparison. So these are the two ways of dealing with the undecidability of real comparison. First way, and that's what we chose here as initially, make it partial. And the second way is make it total but multi-valued. And this can be, we don't need this as separate primitive, because this primitive can be expressed using the partial comparison and the new operation, multi-valued operation of choose. Okay, and now after all this motivation, we can actually start writing some programs. And the first program we want to write is non-extensional integer rounding. Right, as I said, extensional integer rounding must be discontinuous, must be uncomputable. So we relax this by permitting two possible return values for every possible real argument r. So r is a real number, z is a rounded integer, and z must satisfy this condition that it must be between r minus 1 and r plus 1. And the inequalities here are carefully chosen to be strict and non-strict, such that elegantly, now every real number has two possible return values of this round function, which obviously is not a function, but a multifunction, because there are two possible integer return values. And we want to write a program that computes this round multifunction using the primitives that we have just introduced, the partial semantics of test, and the multi-valued choose operation. And the nice thing about these primitives is that they are actually computable. And so by restricting to these primitives, we can make sure that any program that we now write is actually also can be is a computable or computes a computable function. So here's a first example code. So argument the real number r, and the return value is some integer, and we declare and initialize some variables. A real variable x, which is initialized with the argument r, and an integer z, which at the end is going to be the return value of that multifunction. And here's a loop that kind of probes different values, integers z, which one is possible return value, one of the two possible choices. So this loop kind of ramps up the integers, gradually increasing the integer until arriving at an integer that satisfies this condition. Well, satisfy this condition, we cannot have a decidable comparison here, and that's where the choose operation comes in. Namely, as you see here, again, the two arguments to the choose operations are comparisons, real comparisons, and this returns does not return or is unknown if there's an equality. So, but there's an overlap, so that always at least one of the two condition holds, right? So less than r, greater than r minus 1, at least one of them is always true, so that this is defined. And if the first one returns true, then it means we're still in the lower realm. Z is too small to satisfy this condition, so we increase it until finally the loop terminates, because the second condition kicks in. And when the second condition kicks in, then we know really that we have satisfied this. And since this is the first time this condition holds, or at most the second time, because of this overlap, we also immediately see that this condition holds. So this is kind of a linear search for an integer that satisfies this condition by increasing starting with 0. And what if the real number x is negative? Well, for this case, we have a separate similar loop that kind of decreases that to find, again, in this condition case, multi-valued integer rounding. Now, there's one thing that makes this program problematic. Namely, here we have committed the very sin that I've tried to prevent. Namely, we're comparing different types, integers with real numbers, right? So this is not a correct program. Instead, well, we cannot use the integer embedding either, because that would give 2 to the z instead of z as a real number. So instead, what we need to do here is introduce another real variable, whose value is maintained to coincide with its integer. So that's a popular programming trick here. We cannot compare integers to real numbers. If we want to, then introduce another real variables and make its value coincide throughout the computation with this real number. Yes. So yeah, I'll leave it to you to change the code accordingly. And finally, at the end, return z. And it's obvious that this is a way to express the non-extensional integer rounding multifunction as expressed here using this new semantics. And now everything here is rigorous, right? So this is different from naive approaches using floating point computation for integer rounding. But the disadvantage is that it is slow, as you see here, right? It's slow because if we kind of count the number of iterations of this loop, if the real number x has some value like 2 to the n, So it has binary length n. Then this loop will take 2 to the n iterations. So measured in terms of the binary length of the argument or of the return value, this is an exponential time algorithm when we count the number of iterations of the loop. And so how about a more efficient algorithm? Is there a more efficient algorithm? And yes, the answer is yes, there is. And that's our next algorithm here. So here you see the next implementation of the same non-extensional integer rounding with two possible return values. Now we introduce two additional variables in integer b, which is going to be signed digit. So you may recall the signed digit representation for real numbers. And then there's another integer k. So let's look at the code here. And the idea here is to, I mean, naively, we would express or we would extract the integer rounding using a binary search rather than a linear search, right? So this is linear search, right? And you know linear search is bad. And a faster version is binary search, but binary search has again this problem about comparing, which involves comparing numbers and causes all these problems if two numbers coincide and decidability. So instead, we need a kind of multi-valued version of binary search, and this is going to be the signed binary search. Okay, and this program has two loops. First, we kind of try to normalize x to be of magnitude less than 1. So here we repeatedly divide x by 2 to scale it efficiently, right? So that takes a number of iteration that is now linear in the binary length of the real number x, of the real argument r. So this is good. That means it's a polynomial time, many iterations for this loop. And each time we scale x by another factor of 2, we keep track of that in this integer k here, introduced here, so that we keep in mind that the actual original real number is in range minus 2 to the k to plus 2 to the k, right? Okay, so this is basically thinking in terms of binary expansion, means we have shifted everything beyond the binary point. And now we can gradually, in the next loop, gradually recover the bits of x. The first k bits we're going to extract by looking at the first bit after the binary point. But as I said, we cannot extract the binary bit. Instead, we're going to extract the assigned bit using this ternary choose operation, right? So here you see the ternary version of choose with 3 arguments, 3 comparisons. And again, the comparisons are designed carefully to make sure that there's always an overlap, so that there's always at least one of the 3 conditions holds true. X is negative, or x is positive, or x is between -1 and 2. You see here's overlap and here's an overlap, but between those there's not. And and depending on which of the 3 conditions is true, that corresponds to a signed digit. So if the first condition is true, the return value will be 1, -2, meaning the return value will be -1. So if x is negative, this will return negative, signed -1 digit. If x is here in this range, then the second argument will be true of type Kleene, which makes choose return 2, minus 2 returns 0. So in this case, the signed binary digit will be 0. And similar in this case, the signed binary digit will be +1. -1, 0, +1 will be returned value, but in a multi-valued sense because of this overlap. So we cannot predict which one of these will be returned if both of them are true, but in either case, it's going to be a valid signed digit for the first, imagine the first binary digit in front of the binary point being returned here into B. So B is the most significant signed binary digit of X. And so once we've recovered that, we remove that from X, okay? And then, yeah, indicate that we've recovered the first digit and scale X, so to kind of shift in from right the next binary digit in front of the binary point, and observe whether we have already recovered enough bits. So this is kind of our signed bit counter. And we keep the signed bits here in this integer variable z. So as we recover one bit from the real variable x, we shift that into the integer variable z. Namely, we multiply z with 2, but we don't have multiplication by 2, so we add z to itself, right? That's the same thing, shifting in the new signed bit from the right into z. And so this loop, bit by bit, indeed recovers the signed digits, the signed bits of the real number x, and shifts them into the integer z. And in the end, it can return the integer z. And the number of iterations is k, which you recall is basically the binary length of the real argument r. So this is a polynomial time algorithm for efficiently recovering the integer rounding of a given real argument in the non-extensional sense here. Okay, that was our second example code for imperative programming over this new while programming imperative paradigm with the 3-sorted structure. Okay, let's proceed to look at some more such examples. Right, and keep in mind the 2 points made here. So we don't have integer multiplication. Instead, we use integer addition, which is permitted. And we have multi-valuedness as part of the computation. Therefore, also the return value is multi-valued. Our next example is a transcendental function, the exponential function. And we're going to use the following way of approximating the exponential function, namely using its Taylor series. And the mathematical lemma says we can approximate the exponential function if the real argument is not too large, less or equal to 1, using the first p terms of the Taylor expansion, or rather minus p terms, because p is preferably going to be negative, right? The case where p is positive is not really interesting, because in this range, that's going to be a trivial bond. So the interesting case is when p tends to minus infinity, and then this is a positive number, the first kind of p terms of the Taylor expansion. We're going to use that in our implementation. So the same hypothesis here is true. Our real argument x, precision parameter p, imagine p to be negative and very far negative. And yeah, we kind of keep track of these fractions. So j is exactly this variable here, and rj is the real version of j. Remember, because we must not mix types, therefore there's a separate variable for this that we will make sure to mathematically have the same value, but computationally we cannot, we must not compare them or convert them or embed them. Okay, and here's the while loop here for this sum. And initially, the value of the sum is initialized with 0. And initially, the value of this fraction when j is equal to 0, x to the 0 divided by 0 factorial is 1. So that's of initial term. And in the loop, this this initial term gets added to the loop, right? To the sum variable, and then we calculate the next value as j, the sum index increases. How does that change? Well, there's when j is replaced with j plus 1, then there's another factor of x coming here, and another factor of j plus 1 coming here. But right, observe that here, right, we increase j, and we also increase the real version of j. As I said, we will maintain that integer and real version always mathematically have the same value. And then we adjust that temporarily variable for this fraction accordingly, multiply it with another power of x here for the numerator, and divide with another, with rj, the real version. We cannot use the integer version because that would be a mix of types in this expression. So we divide by the real version, and that's it, right? And after the first, according to the lemma, if we use the first minus p terms of that series, then we're done. Okay. So yeah, that's a rigorous way of implementing the exponential function. And let me point out, this is the way that one really thinks about the exponential function mathematically, right? One thinks of it as the limit of this Taylor series and approximated by the first minus p terms. And there's no string computation involved, no sequence of approximations. So this is really convenient, that this is intuitive, and it is rigorous. Convenient, intuitive, and rigorous. And let me point out the semantics that is yet informal here. Namely, arguments are considered given exactly. So the real number x is here exactly. We don't need to, that's one of the purposes, to worry about rounding errors. And the return value is approximated, but approximated up to some guaranteed error 2 to the p, where p is now here this integer parameter, right? So this is a program computing the exponential function as a function from real numbers. Well, not too large real numbers, to real numbers. And while the mathematical exponential function has one argument of type real, its program has two arguments, the mathematical argument real and an additional integer precision parameter. Good. Yeah. So this is how one really intuitively writes numerical code, right? Now, what if the integer real parameter x is greater than 1? Well, then numerically, standard way is to use the functional equation of the exponential function to reduce it to that, right? So first recover the integer part of the real argument, and then repeatedly multiply Euler's constant E that many times, and then treat the non-integer part. And this is exactly what this implementation is for the non-integer part of the argument, and the integer part can be dealt with in this way. And how can we extract the integer part? Well, that's what we just talked about in the previous slide with the multi-valued rounding function, right? That's exactly the point here. So I leave it to you to actually make that part also rigorous by combining the multi-valued integer rounding function from the previous slide with this restricted version. Okay, that was our third example program of imperative programming in this rigorous paradigm. Let's now move on to some computing some functional, namely the root of functional, the root of a fixed given function. And let me recall for your convenience how we what we established about the computability of that functional, because that will of course be the constraint to actually writing programs for it. And so the classical mathematical intermediate value theorem says any function on the unit interval that is negative on one end and positive on the other has a root, possibly many, possibly uncountably many, and like in this example. But in general, without further conditions, we cannot compute that root because it can jump discontinuously. But if we restrict to simple roots, then we can use this variant of bisection, which is trisection. So the bisection considers the two cases, looking at the value of the function and the sign of the function value on the midpoint. If that is positive, then proceed to the left part, and otherwise recurs to the right part. But if the function value is actually 0 on the midpoint, then we're in trouble because that's undecidable. And in our proof, mathematical proof, we could kind of exclude that case by separately treating whether the root is a dyadic rational or not. But when implementing it, we're going to use a different approach, namely, we're going to use the hypothesis that the function under consideration has a simple root. Okay, so this is another way of avoiding this kind of discontinuity, right? So here you see discontinuity is due to the function having non-simple roots, namely this whole hovering part. But here we impose, as another way of avoiding this discontinuity, we impose the hypothesis that the function has a simple root, and moreover that this is the unique root of the function. And then we can actually convert the previous algorithm into a while program using trisection. So let me show that. In this case, we have again the argument is now argument of type real function from the unit interval to the reals, and we have the same precision parameter as previously. And the hypothesis is that the function is negative on the left end and positive on the right end of the interval from x to y, and that this function has only one zero, that this is unique, and this says that the root must be a simple root. And here's an example. And in trisection, right, we don't test for the value sign of the function in the midpoint, because that could be the root. Now we don't know whether it's not. So instead, we're going to, that's one point of trisection, determine the sign of the function value at 1/3 and at 2/3 of the interval. And by the hypothesis that the root is unique, at most one of them can be a root, right? If both of them are a root, then we have two roots, which contradicts the hypothesis that the root is unique. So by imposing the condition that on this the root is unique, we can make sure that at most one, possibly none, but at most one of them is a root, and the other therefore has either positive or negative sign, which can be determined, right? So signs of real numbers can be determined, provided that the real number is non-zero. So here the sign can be determined, In this example, this sign cannot be determined, but when we are going to construct choose operation in a suitable way by choose operation to determine both signs, then we can make sure that at least one sign is actually computationally known, and therefore the choose operation will return a value. So here it is, here's our code. So we initialize the left and right interval bound with 0 and 1. And while the interval size is too large, we keep applying the trisection, reducing the interval size by a factor of 2/3. And only if the interval has become sufficiently small, then we return then we have sufficiently approximated the root sufficiently well and can return it. So this is again the same semantics as previously. Arguments, in this case a real function, are given exactly, and the return value is an approximation of the error 2 to the p, where p is this additional integer parameter that is not present in the mathematical formulation of this function. Mathematically, trisection would receive a function and return a real number as root of that function, and computationally there's an additional precision parameter integer p. Okay, so now in this while loop, we perform exactly this trisection method with the choose operation. So we have two chooses here. First choose is if the interval size is just on the border, on the boundary of we want it to be at most 2 to the p, and if it is equal, the interval length is equal to 2 to the p, then this comparison would freeze, would stall. So we instead use an additional comparison with an overlap between both to make sure that this at least one of the two conditions always holds, and therefore make this choose totally defined. And similarly, inside the loop, we determine the signs of the function at both points. 1/3, well, that's the general version if the interval ranges from x to y, 1/3, and 2/3. And again, this when the first case hits, if the function value is negative here, then we recurse to the right 2/3. If the function value is positive here, then we recurse to the left 2/3. You see that here. In the first case, we increase x from here to 1/3, or this. In the second case, we decrease y from 1 to 2/3, or this value. And this condition has been carefully construed such that at least one of the two cases is always true, because if both are true, what does that mean? The function, it means the function is negative here and positive here. No, if both are false, then that means the function is positive here and negative here. So positive here, negative here. Then we know mathematically by intermediate value theorem that there must be another root which contradicts our hypothesis that the function has a unique simple root. So from this hypothesis, it follows that at least one of the two conditions always holds, and therefore is fully and well defined. Okay, so yeah, that's a rigorous implementation of a simple, unique root finding using this imperative programming and with the trisection. And here we see that there are two calls to the choose operation, two ways of introducing multivaluedness during the computation. The return value will in either case be an approximation to the actual root up to error 2 to the p at least. Okay, good. So that's this example. And um, final example is about matrix determinant computation. Again, a classical topic in standard numerics. If we compute the matrix using the Leibniz formula, that's an exponential time algorithm because it runs over all the sum over all permutations. So we don't want that. So numerically, the popular way is to use instead first Gaussian elimination to bring the matrix to echelon form, and then multiply the entries on the diagonal of the matrix, right? So bring the matrix to triangular form and then multiply the entries on the diagonal. That's the determinant, right? But Gaussian elimination, as you already all know, has this problem about the pivot search, right? So Gaussian elimination uh, uh, is sometimes used to determine the rank of a matrix manually, right? But this involves determining whether an entry is zero or non-zero to check whether it can be used as a pivot or not. And this is exactly what makes standard Gaussian elimination uncomputable. So we cannot implement that in the naive way. So instead, we here use a variant which supposes that the initial matrix is regular. Uh, right? If the original matrix is not regular, then the determinant is zero anyway. So that's not an interesting case. And then we adapt full pivoting to uh, Gaussian elimination with full pivoting and make sure that we don't need to test for equality in pivot search as follows. So first, you see here the algorithm, standard full pivoting algorithm. Namely, so here we have three integer variables that run over the cubic running time of Gaussian elimination, right? And here we have the current pivots, Pi and Pj, row and column position of the pivot. And this is the value of the determinant as we keep calculating. This is what will be returned at the very end of that function. So here the function involves an integer parameter, but we're not going to use that. We're going to calculate the determinant exactly, but still technically it's present here. So, and here we have our standard loop, right? So we run over the columns. This is the column index, and try to find a pivot in the submatrix that starts with column K up to the last column, and in the row starting with row number K up to the bottom row. Okay, so lower square matrix starting with row column number K, and as K, right? So the indices range from, in this two-dimensional array, range from 0 to d minus 1. That's array indexing starting with 0. And here we find a pivot, and how to do that will be the subject of the next slide. But here we find the index, column and row index of a pivot. Pivot meaning an element which is non-zero. And then we do our regular, just standard Gaussian elimination, multiply the temporary determinant with the current value of that pivot, and make the row, which we've just found, swap it with the current row, the row where we found the pivot, and also swap the column where we found the pivot with the current column, right? So we do both column and row swapping. Yeah, that's the whole point of having full pivoting, right? Not just rows, but also column. And if the yeah, if that's an actual swap, then since the determinant is alternating, that means the sign of the determinant changes, right? So here you see a sign flip, and here you see another possible sign flip unless the pivot is actually in the current row. Okay, and yeah, then we just continue as with regular Gaussian elimination, scale the row where we found the pivot, which is now the current row after the swapping, to make the pivot 1, right? So like this, scale it. And in all sub rows below that, subtract the accordingly so that the current column becomes a column of zeros. Right? So here you see the standard approach, and you see the 3 loops, nested loops that give rise to the standard cubic running time. And yeah, that's basically it. So yeah, basically this that's a nice thing. You can just write down full Gaussian elimination with full pivoting in the way you would, right? And don't need to worry about any rounding errors or other problems. The only thing is that is here kept in red is how to find the pivot. And this is where classically problems arise. But the first thing is because of our hypothesis that the matrix is regular, since we use full pivoting, it is guaranteed that there exists a pivot. That's important, right? If we were to drop the regularity hypothesis, then maybe there is no pivot, obviously, right? Or if we were to use only column swapping and not, or only row swapping, then still there's no guarantee that we can find a pivot in this square submatrix. That's important, square submatrix. But since we use full pivoting and under this hypothesis, there will always be a pivot, and it remains for us to find it. And we're going to do that in the multivariate way as follows. So this is going to be a piece of code that is to be replaced with the red part. So here we look for a non-zero element in the submatrix, starting with row k and column number k. Anything that is greater than the current, or actually we're looking for a maximal pivot value. So here we look, and all entries in this square submatrix, column and row, and calculate the maximum value of all entries in that submatrix. What is the largest entry by magnitude? And then again we look at where that maximum value is attained, but of course we cannot take for equality whether it is really attained. Instead, we check whether the value is somewhere between half the maximum and less the maximum. And again, you see that there's an overlap. We know that at least one of the two conditions is always satisfied, and therefore making this choose invocation of choose the total computation. And if it's the second case, if we find a position where the value is actually at least twice the maximum, then this is what we use and return as pivot value for the rest of the Gaussian elimination. Okay, so here's the multi-valued nest in the pivot search. Good, so Gaussian elimination for matrix computation. And in the remaining few minutes, we want to finally formalize what is a while program over this 3-sorted structure. Here's the 3-sorted structure with this error embedding, and a while program for this structure that computes a function with d real arguments and e integer values is formalized as a program which receives e integer arguments and d real arguments exactly. So that's important. No worry about rounding errors. Real arguments are exact. And then there's this additional dedicated integer precision parameter p, which in the mathematical function does not occur, but in the while program is passed to indicate up to what error the function value should be calculated. And then, so this is the declaration of this while program. Additional integer parameter p, real arguments, integer arguments. And then the program can use some local variables constant number of local variables of all three possible types, integer, real, and Kleene, and then proceeds to perform calculations on integers without multiplication and calculations on real numbers with multiplication exactly without rounding errors. Only thing is that the tests are now partial, which means that the return value in a lazy sense is now of type Kleene. And to deal with that, the programmer is allowed to use this multi-valued choose operation. And it's the programmer's responsibility to make sure that at least one of the arguments is true so that the choose invocation is actually well defined. And at the end of the computation, the program must return some approximation. So that's kind of the schizophrenia of this programming paradigm. Arguments are provided exactly. Return values only need to be approximated, but approximated up to an absolute error, which is indicated by the precision parameter, which we rewrite in this embedding as I of p, which means short for 2 to the p. Provided that the arguments belong to the domain of the function. If the arguments do not belong to the domain, then the computation can do anything it likes, like we defined and considered in stream real computability. And why is that a great paradigm? Why does it replace all the stream computation? Because, and that's the final slide, this programming in this sense is actually Turing complete. That means programs with this syntax and semantic can express precisely the computable partial functions, computable in the sense that we just investigated previously, and only. So this means this is an equivalent way, but much more convenient and much more tailored to numerical program thinking. So, and right, let's prove or indicate the sketch of that important theorem. So the practical application, it means we don't need to worry about these streams anymore when we actually write programs, but we can do that in this way, and we can be sure that any program we write here is actually a computable function, and conversely, any computable function can be expressed in this way. So one direction, if a program is expressed in this way, since we know that real arithmetic operations are computable and the partial tests are computable and the multi-valued choose operation, then by structural induction, it means that also the entire sequence of executions of this algorithm represents a computable real function. And the final thing is about the return value. The computation returns only an approximation, but since the limit of fast converging sequences is computable, then that means that also the result value is again computable. That's one direction. And for the converse direction, recall our definition, what originally it means to stream compute a real function. And also let's recall the rounding multifunction. And now we need to express that computation using this three-sorted structure. The only thing to observe is in the stream computation, we only deal with integer numerators to approximation. In the while program, we really actually deal with real numbers. So how can we recover the approximation? And this is what the multi-valued rounding function allows. Scale the real argument with 2 to the m, and then use the round multifunction, and this is going to be our integer numerator of the argument. And then we can perform the other computational steps just as in the stream computation. So yeah, that's our advertisement for this while programming over this three-sorted structure. And to conclude, We talked about imperative programming over the reals using while programs. We recalled while programs over natural numbers. We considered but had to discard while programs over the real numbers because they cannot include the integers. Instead, we would consider while programming over three-sorted structure. We're including the Kleene logic, three-valued logic extending the Boolean logic with this new unknown value, which is different from mathematically undefined. We consider two versions of non-extensional integer rounding. It must be non-extensional to make it computable. First, a naive that would perform a linear search for the integer part, and then fast version, which would not involve binary search because that would involve undecidability, but instead signed binary search. And we saw a program that realizes the exponential function using rigorous approximation. We saw an example program that implements trisection for simple root finding using choose operation in two cases. We saw a matrix determinant computation with multi-valued pivoting, full pivoting with multi-valued pivot search to avoid the trap of having to compare for interest for 0. And finally, we saw proof sketch in the statement that programming in this sense is actually Turing complete. So that's all for today. Thanks for your attention, and yeah, see you next time.